Hello. So I'm back with another application of the discrete time Fourier transform. This time we're going to look at the fractional delay. Okay. So if you remember, one the simplest way to understand the relationship between the continuous time signal and the discrete time signal is wherever you have an impulse, always imagine that there is a little sink sitting, and the sink goes to 0 at every other stem location. So if there is another impulse over here, this goes to 0, and this guy has its own sink. So this guy has his own sink which goes to 0 at the other stem locations, and so on. So this is the cleanest way to understand the relationship between the discrete time and the continuous time. So given that this is the case, one nice way to just characterize this relationship is just to say that if you have the signal delta n, that directly yields something like sink of t. Okay, sink of technically fst modulo scaling, there needs to be a scaling, but I am ignoring that. So that means if you have n minus 1, that is just a delay of exactly t or 1 upon fs. So this corresponds to sink of fs into t minus 1 upon fs. That is just sink of fst minus 1. So this way you can use linearity and linear combinations to arrive at the reconstruction. Okay, in essence this is just the low pass filtering, and this will give you the answer. Okay. Now that we have this information in the back of our mind, let us actually look at one of the example problem that was given to you. Okay, I'm going to take a slight modification. Let me give you this filter. Let's say e power minus j 3 omega. This was given to you. Okay. Now how do we understand this? So if you know the properties of the DTFT, the properties of the DTFT tell you that e power minus j n omega m omega corresponds to delta of omega minus 3. Okay, so this corresponds to delta of n minus 3. If you don't believe me, if you use the inverse DTFT formula, this if you do 1 by 2 pi integral minus pi to pi e power minus j 3 omega e power j omega n d omega, okay, you will basically get this to be 1 upon 2 pi integral minus pi to pi e power j omega n minus 3 d omega, and if you simplify this you will end up getting sine pi n minus 3 by pi n minus 3. Of course, the n is equal to 3 case has to be handled carefully. So for n is equal to 3, you get 1. For every other integer, you know that sine of an integer value of pi is 0, which means that this sequence is the exact same as delta of n minus 3. So do not be shocked when you see these two. These two are the exact same thing. Of course, be careful when you substitute n is equal to 3, the 0 by 0 implicitly means you have to either use limits or you evaluate the integral carefully. Either way you get 1, which means that e power minus j 3 omega corresponds to just a delay of 3. Okay. Now this is something which is okay, which is reasonably easy to understand. But in one of the questions we had something like this, a slight vary, but let's say h of e power j omega is given to be e power minus j omega by 2. Now in this case it is tempting to write, I will write it in a different color, delta of n minus 2. This is completely wrong. Sorry, it's not delta n minus 2, n minus half rather. This is completely incorrect, because the discrete time sequence actually has to take only integer values, and you can't have half and things like that inside. So this is not the way to do it. Okay. Of course, we are going to look at our intuition and try to understand, but if we don't know what to do, let us actually use the blind approach, which is to just directly use inverse GTFT formula. So what do? We say one upon 2 pi integral minus pi to pi e power minus j omega by 2 e power j omega n d omega. This is equal to integral e power j omega n minus half d omega between minus pi and pi, and if you simplify this carefully, you will end up getting sin pi n minus half by pi n minus half. In fact, for a more general case, if you do e power minus j omega alpha, you will get sin pi n minus alpha by pi n minus alpha, okay, which is interesting. This is actually reminiscent of something like the low pass filter, but the cutoff seems to be pi, right? So this, see, because sin omega cn by pi n delayed by alpha roughly. Okay, the problem is alpha is not necessarily an integer, it can be any real number. So given that this is the case, what are we to understand from this? So e power minus j omega by 2 corresponds to a delay of half a sample, whatever that's supposed to be. If we use the DTFT, we get sin pi n minus half by n minus half. This is not equal to something like delta by n minus half, because as one of you have mentioned, this does correspond to some sequence which is non-trivial, meaning it's defined for all values. Let us directly try to plot it. Okay, let's actually just open Python. Okay, just 1 second, and try to plot it. So while we are at it, notice that if alpha is an integer, then it becomes very easy. If alpha is integer, this just collapses to delta of n minus alpha. The problem arises only when alpha is not an integer. Okay, so if we'll import numpy, okay, we'll import POLab. We'll also get our favorite FREQZ. Okay, so now let's actually look at a truncated version of this sequence. Okay, we will take alpha to be 0.5, and then let's evaluate. Okay, now I'm just going to do np sine of np dot pi into n minus alpha by pi np dot pi n minus alpha. There will be no divide by 0 over here, for an alpha is not an integer, so there's no problem. Let's actually look at the frequency response of H. Okay, now there is some bit of oscillation on over here. Okay, let's ignore that. It looks flat. It looks reasonably flat, which is not surprising, because mod of H e power minus j omega alpha is 1. So this is what is called an all pass filter. Its gain is actually unity. Okay, its gain is actually unity. Okay, let's actually look at the time domain response. Again, this looks like a sink. It looks like a sink. Okay, it looks like a sink, but notice there is some bit of symmetry over here. Okay, there's two little dots over here, and things like that. Let's actually, instead of stem, use plot and see what we get. Okay, so let's look over here. Okay, it looks like a sink. Okay, let's actually do something a little more. Okay, let's take just 100 points. Yeah, it looks like a sink. Let's choose an alpha which is not 0.5. Let's choose something like 1/3. And then let's have a look. Now notice that we get a different sink. In fact, if you look at the stem plot, you'll find that this is a different sink which is actually not symmetric about 0. It's not symmetric. There is some bit of asymmetry about it. So this looks very mysterious. Okay, what is happening? We are getting different responses. Of course, I'm showing you a truncated version, but we are getting different responses based on different values of alpha. And why am I preemptively calling it fractional delay? Now this mystery will be absolutely clear to you if you just remember what the original delta n actually corresponds to. So I will draw it and show you. So this e power minus j omega alpha corresponds to a delay of alpha, correct? But what does alpha mean? It's alpha times t in the continuous time. So let's actually take delta n and then act on this. So if you take delta n, okay, this delta n, but delta n, if you remember, actually corresponds to a sink. Okay, let me draw these points. Okay, the sink goes like this, over here. A very poorly drawn sink, but it's a sink. Let me just, I'll cheat by copying this object, okay, and pasting it, and then I can try to maybe just flip it. Okay, let me not do all that. I actually just directly just draw the other part very in a nice way. Okay, so this is n is equal to 0. This is 1 minus 1, and in continuous time lingo this is 0 t minus t. So what are we doing by when we do e power minus j alpha? We are actually changing the location of sampling. So over here the location of sampling is actually this. When we evaluate, when we actually convolve this with the filter whose response is e power minus j omega alpha, we are actually changing and sampling it at this point, at this point, at this point, at this point, and so on. Actually, it's exactly at those. You don't believe me? Have a look over here. I'll set alpha to be half, and we'll look at the filter again. If you look at the stem plot, you can see as you close in, first things first, the value is over here, just both of these are symmetric, and then it goes negative and then positive again, which is exactly as I had predicted over here. Okay, the value over here is positive, then goes negative, and then again goes positive after this, which you can see by drawing the other one. So it's positive, negative, then positive, and then negative, and so on. This is exactly what happens if you move the sampling point by half. Okay, but what is the iteration? How does this e power minus j omega alpha, where alpha is a fraction, correspond to this? Now, if you believe that integer delays actually correspond to next points, meaning every integer delay is a delay by t seconds in the continuous time, then a fractional delay is actually a delay of alpha t, which means that if you look at the actual continuous time signal, this corresponds to a change of location of sampling. This corresponds to a change of location of sampling. Basically, you are actually going to perform the sampling at a different point. If you take the 1/3, then t by 3 will be this point, and t minus 2t by 3 will be this point, which is why you got this kind of asymmetric approach when you took 1/3. Don't believe me? You don't need to believe me. You can try this out for yourself. Okay, let's say 1/3. Okay, so let me zoom in and show you. Okay, so let's see, this is, oh, I have to go to 0 point, I'm sorry, yeah, the symmetric point is over here. So 100 is, yeah, so over here this is the middle, over here it's at the 1/3 point, here it's the minus 2 by 3 t point. So this is essentially what is happening with the fractional delay. Now, to actually believe that this is indeed the fractional delay, here is one way to look at it. Okay, so if you look at the discrete time Fourier transform, remember what is the discrete time Fourier transform? It is the relabeled version of the continuous time Fourier transform of the sampled signal. Okay, it's the relabeled version of the continuous time Fourier transform of the sampled signal. Okay, great. So then, if you look at the continuous time Fourier transform, okay, between minus pi and pi, the magnitude response of the so-called fractional delay is actually flat. Okay, what about the phase response? This is where things get interesting. In the phase response, okay, we chose something like e power j minus j omega by 2. So it's actually at minus pi and plus pi, it starts at minus pi by 2, goes to pi by 2. I'm sorry, starts at pi by 2, goes to minus pi by 2. So in fact, minus pi by 2 is the value here, pi by 2 is the value here. So this is the phase response. Now what is the relationship between this and the continuous time? So remember, in the continuous time, this corresponds to the frequency, let me write it in a different color, minus fs by 2. This corresponds to the frequency fs by 2. Similarly, these phases are also corresponding to certain time notations. So which means that this pi by 2 and minus pi by 2 are going to correspond to actually some time. So remember, the notation is one phase is capital T. So pi by 2 and minus pi by 2 are going to correspond to, so basically 2 pi corresponds to capital T and the difference of pi corresponds to T by 2. So this is one way you can get an interpretation of the continuous time. Basically I'm just trying to point out that this extra part is T by 2 because that's pi. 2 pi corresponds to T in the time domain, and pi, pi corresponds to T by 2. This is another way of understanding. But this is a little more complicated. The better way is, again, remember, if you see this picture, I've drawn a picture for you. You see this picture. This picture makes it adequately clear because I'm essentially plotting a sink along with the sampling location. So this is basically the sampling location, and I'm actually plotting I'm keeping the sink constant, I'm changing the sampling location and plotting for you the exact location of the the xn, which is the so-called fractional delay. So if you actually trace out for various values of alpha, I'm changing alpha from 0 to 0.99, you see that it actually traces the shape of the sink. So what implicitly is occurring is that when you perform this convolution with e power minus j omega alpha, you are actually redrawing the continuous time signal, which is this dotted line, which is the sink, changing the location of the sampling by a factor of alpha times t, and then coming back to the discrete time domain. So you can see this in action very clearly. If you I'll pause it. If you look here, exactly if you sample at the right point, you're going to get exactly sine pi n by pi n, which is delta n. If you move about, let me move about, let's say halfway. I think halfway will be right here. Okay. I think I don't have the halfway frame over here because I think halfway. You can see that you are exactly getting the shape which I got. You are exactly getting these, And if you move slightly further than halfway, you will find that you're again tracing the same shape out. And if you go to the end, you're essentially just going to miss out on, okay, I'm sorry. It's going to miss out on, if you go to the absolute end, you're going back to the beginning. Okay, you're going to go, this 1.00t is almost the same as the original sequence, except that that's a delay of one sample. So this alpha actually performs sync interpolation and resampling implicitly. Now, what is the use? The use of this is that you can actually resample without reconstruction. You can actually resample without reconstruction, meaning that you can actually perform the resampling without having the reconstruction. You don't have to come back to the continuous time domain and sample again. You can perform completely digital filtering to change the location of sampling. Okay, so in fact, we can do so this is the key advantage of using the fractional delay. This has lots of applications in things like multi-rate signal processing, where you are actually going to deal with different rates of signals. And one important point is, again, you can check the stability. You will find that there are stability issues with these filters, and even more importantly, these filters are not realizable because of their double infinite length, which means that, again, for practical realizability, the only way to get around it is to use a truncated version or a windowed version. That's the only way. And the moment you're going to use truncation or windowing, you're going to introduce frequency domain artifacts, as we have seen in the previous video. That is something you have to keep in mind. Okay, thank you.